Hello, welcome to the course Electronic System Design. Earlier lectures we were discussing about the combinational logic gates, where we have two types of gates. One is the static logic gates and one is the dynamic logic gates. And we saw that static logic gates, the output is always connected to either ground or VDD, and we have two networks, one is pull up network and the pull down network, to pull up the output node high and low respectively. So, that was static CMOS gate, and then we saw dynamic CMOS gate, where we have a output node which has certain parasitic capacitance, or we can even intentionally make it a little bigger and have a significant capacitance, and we use this capacitance to store the charge in the pre-charge cycle, where we have a pull up network only made up of the single PMOS. That PMOS is used to put the charge on this capacitor. Now, in the evaluation phase, depending upon the input, whether this node is pulled down to 0 or need not to pull down to 0, based on that, pull down network will act. It will turn on to pull down the node, or it will remain off and the output will be kept as it is to high supply voltage. So, these are the two gates which we saw. These are combinational logic gates. What is a combinational logic gates? We have the output which is dependent only on the current state of inputs. We have three inputs, for example, A, B and C. So, the output is dependent only on the pattern of these three input values. If it is 0 0 0, the output is very well defined for this. If the input is 0 1 0, output is very well defined for this pattern. So, that is a combinational logic gates. However, the second types of gates we have sequential logic gates, which we are going to discuss today. That now the logic network we have, some of the inputs are there and based on that we have a output, but some of the outputs of this logic circuits are fed back to the input of the same circuit. So, for example, we have a feedback network in this, very much like a control system. So, this feedback network takes some of the outputs and feed it as a input to the logic circuits. So, now in this case the output not only depend on the input pattern, but also the previous stage output. In the previous stage, whatever was the input, in the current state that act as a input to the circuit. So, whatever in the, let us say we have two states. In the very first state we have certain input pattern. According to this, some output will be generated. In this current state, some of the output are acting like a input, and of course input has its own pattern. So, the current output depends on the current inputs as well as the output of the previous state, which is fed back at the input. So, that is a sequential logic gates, where we have this type of feedback network. It means that the system has some sort of memory of its previous state. However, in the combinational logic, only the state is dependent only on the present input. However, in sequential, it is dependent on present as well as previous state. Previous state means the system now has started having some sort of memory elements. This memory element is the output of the previous state. So, we can say the system now has some kind of memory in itself, or the feedback network in itself. Let us see how the sequential logics look like. In sequential logic, we have a main logic block which is still the combinational logic. This has set of inputs. Accordingly, we have outputs, and then we have some of the output which are fed back to the input. So this is your feedback circuit. Most of the time this can be a D register, D flip flop or D register. So here we have inputs. Inputs can be more than one vectors A, B, C, D. Then we have the output, and some of the outputs are actually fed back to the input and act like a current state. This is our register, and this is our simple combinational logic circuit. So this is the simple structure of a sequential logic gate. The combinational logic circuit is very well similar to our last discussion. In the last 2-3 lectures we discussed combinational logic gate. This can be a static logic gate or a dynamic logic gate, and now some of the output is fed back to the input through this feedback element, and this feedback element can be of two types again. It can be a latch and it can be a register. So let's see what's the difference between these two. So this can be a latch or it can be a register. So what's the difference between these two? A latch is a memory element. It can store its state for some time, and this latch is the level sensitive. And the register is a edge triggered element. So now we have this feedback network which is of having two types. One is we can implement it using a latch, and the other one is we can implement using a register. So what is the difference? Both are memory element, both can store its state. For example, if we write the bit 1 here, these latches or these registers can remember this bit 1 over a period of time till we again want to reset it to some other value 0, or we want to keep it to 1. So, latch and register both can keep the value. However, the latch is level sensitive, means if the input which we are using to write the level in the latch, this input is changed to a high state, that high will be written in the latch. If the input is changed to 0, that 0 will be written in the latch. So, it is as simple as that. However, the register is edge triggered. So, we have, for example, a clock, we have clock signal. So, whatever is the input state, it will not be written in the register till the clock comes. When the clock, for example, the clock is 0, so whatever is the input changing, it is not going to be remembered by the register. When this clock will go from 0 to high, at that edge this register will be triggered and the input will be written into the register. So, this is the difference between these two. So, we have a, for example, a latch which will keep reading the input data and remembering that as a latch. However, in the register, data will be written only when we want it to be written in the register. So, we will toggle the clock, that time only the data will be written into the register. So, this is the difference between these two, and we have a clock signal which is used for synchronizing all these data writing and reading in the circuit. So, now we come to a point where we are discussing something called clock. So, when we make a complicated system, we have so many circuits to take care of, and all these circuits are connected to each other in some series or in some parallel. There are some parallel paths, some series path, and we need to adjust the timings, because all the circuits have different delays. So, we cannot guarantee that one input is changed at some place, what time this output will, this input will reach to the output. And if we need, let us say we want two output from two different blocks, one block has 100 picosecond delay, the another has 200 picosecond delay. So, we want both of the output at the same time. So, we have to synchronize both of the outputs so that we can use both of the output and calculate our whatever function in the next state. So, this output should be available to us at the same time, but the delays are independent to our this analysis, and delays are dependent on the circuits, whatever circuit is inside those blocks. 100 picosecond has 100 picosecond delay and the second has 200 picosecond. So, what do we do that all the data which comes to my next state, that is the updated data and not I am using the previous data. For example, if I have 100 picosecond and 200 picosecond, I change the input to these blocks. First block will produce its output at 100 picosecond. However, the second block takes 200 picosecond. The output is still not updated. If I use this data at 100 picosecond only, then I will be using the incorrect data, because the 200 picosecond block is yet to produce its output. So, the whatever the data it has at the output, it is of the previous state, not what I want in this state. So, here come to a point that we use a synchronizing signal which we call clock in the synchronous or sequential logics. This clock is kind of a universal synchronizing signal which we use at the top level, and we synchronize all our circuits, all our data propagation with respect to this clock. So, this clock is a kind of universal clock, and everything, the data coming in, data coming out, that is synchronized through this clock. So, now we have some definitions for data as well as clock. So, when the clock comes, at what time data should be ready, and after clock, how much time data should be available. So, then we have some definitions which are very important definition in synchronous design or sequential logic design. These are setup time and hold time of these circuits. So, let us see what a setup time and hold time of sequential circuits are. So, in timing analysis, we synchronize through clock signal. Now, let us see, we have a clock signal. So, let us say this is clock CLK, this is time axis, and we have clock something like this. This is how the clock look like. It has high time for which the clock is high, then we have off time where this clock is low, and then we have transition. So, the clock is not very sharp because there are so many places this clock is going on, and because of very heavy capacitive loading at the clock generally does not have very sharp rise and fall edges. So, these are fall and these are rise edges of the clock. Now, we see the data which comes at the input of my circuit. Let us say this is my data which is changing its polarity at some point here, going from high to low or low to high depending upon various bits, and then it is stable for some time, and then again it can change. This is D, and then this is the duration where the data is not changing. It means the data is stable here. Then we have the Q, which is output. it's something like this. This is where the data is stable. And this we have made, let's say, for D type register, which we just saw in the last slide. We have this clock signal at this place. Then we have D. D is the input to this register, and then we have Q, which is the output. Now if we see here, the clock is rising at this point. So this is the point where this data will be written in the register. As we just discussed last slide, that register is a edge sensitive or edge triggered block. So this is the rising edge of clock where this data should be read by this register. Now we have two definitions. One is before this time instance of this rising clock, my input data, whatever I am planning to write in the register, that should be stable. It should not be fluctuating or it should not be changing its transition. Before this clock arrives, my all the data should be stable, and the time before this rising edge, for that much time the data should be stable. That time is called the setup time. So this is that instance of writing. Before this, my data should be stable. Let's say at this point my data is stable, after that it's not changing. So this time is my setup time. So my data is stable before this instance, that's setup time. And when this rising edge comes and my data will be now propagated to inside the D flip flop or this register, then for how long the input should still remain stable so that it is satisfactorily read by the register. So that timing is also important, that is the hold time. So for example, this is the instance, and after this, for how long this data should be stable so that it is read properly by the register. This is hold time, T hold. So these are the two critical parameters for the timing analysis. One is the setup time and second is the hold time. Let's write the definition for them. So the setup time the minimum amount of time before the clock edge that the data input should be stable. before the clock edge at the data input must be stable. This is the definition of setup time. Similarly, the hold time the minimum amount of time after the clock edge that the data input must be stable. After the clock edge, that the data input must remain stable. So these are the two definitions of setup time and hold time, which dictates that when the clock comes, which is a universal clock used for synchronization, before this clock and after this clock, for certain amount of times the data should be stable, so that there is no glitches mistakenly read by the register or flip flop. So when the clock comes in, all the data are at the stable state. As soon as the clock comes in, that data will be read by the register, and because it takes time in reading this data and producing the output, for certain amount of time this input data must be there, so that it is satisfactorily latched inside, or if there is a latch or some memory element, it takes time in storing that data. So that is why after the clock there is a hold time constraint for which the input should be stable and it is satisfactorily stored in the register, flip flop, or those circuits. So we have now two definitions, setup time and hold time. Now we see how do we make these kind of latches which can store the data. So up to now we have discussed combinational logic, for example inverter, NAND gate, NOR gate. The output depends only on the input state, it does not store any data. As soon as the input changed, the output will be changed immediately, of course after some certain delay, but the output will be immediately changed, it cannot sustain its previous values. Now let us see how can we make such circuits which can remember its previous state as long as they are active. Once we write a certain signal into these circuits, that signal remains there unless we change it to the some other value. So they can remember or retain their states. So that is called latch or flip flop. So let us see how do we design them. So let us discuss something which is called the positive feedback or bistability in the circuit. Okay, so the very basic bistable circuit which has positive feedback, it is a cross coupled inverter. So for example, we have two inverters in this case. These are symbol of two inverters, and what we do in this case, we connect output of one to the input of other and the output of the second one to the input of first one. So let's say this is my first inverter, this is my second inverter. So the output of first is connected to input of second, and the output of second is fed back to the input of 1. So now we have here Vi1 and this V output 1, which is equal to V output 1 is equal to V input of 2, and similarly here this V output 2, this V output 2 is equal to V input of 1. So the output of one is the input of the other transistor. This is how a bistable CMOS circuit look like, and if we draw the schematic, that looks something like this. We have this is one inverter, this is second inverter, so we connect output of first to the input of second and the output of second to the input of first. So this is how a bistable CMOS circuit look like. If we analyze it, this is PMOS 1, this is NMOS of first transistor, first inverter, this is PMOS of second inverter, and this is NMOS of second inverter. Now let's analyze the first inverter. So for first inverter, we have discussed the voltage transfer characteristics or VTC, which is nothing but V output 1 versus V input of 1, and we saw that VTC few lectures back. It looks something like this. This gradually decreases from high to low. For the input is low, the output is high, and when the input is high, the output is low. So this is the VTC characteristic of the first one, the first inverter. We draw the VTC of the second inverter, that looks something like this. We draw it is little different. V output 2 is like here, and V input 2 is like this, so that we can combine it in a single graph, because we know that V output 1 is equal to V input 2. This V output 1, this V output 1 is equal to V input 2, so that's why we are writing in such a way: V output 1 is on the y axis. So, here we are writing V input 2 as a y axis, and similarly for the x axis. So, if we draw this VTC characteristic for this second inverter, this looks something like this. For low value of input, the output is high, and when we increase the input, the output gradually goes down to 0, and this is a gradual change depending upon the gain of this inverter. Now, if we combine these two graphs, because now these two inverters are connected together, so that V output 1 is equal to V input 2 and V input 1 is V output 2. If we combine it and make a single graph, here we write V input 1, which is equal to V output 2, and here we write V output 1 is equal to V input 2. So, the graph looks something like this. 1 is the characteristic of the first one, and this is the characteristic of second one. So, something like this, the VTC of combined this bistable cross coupled CMOS inverter look like, and this we call it a butterfly curve or butterfly graph, which shows two different paths for going from high to low or low to high. If we see closely, for the single x axis, let us say at one point at the x, we have two distinct value of y. So, whenever we come up with this kind of graph where we have two different paths of going up and coming down, then it means that the system has some amount of hysteresis. And whenever the circuit has hysteresis, hysteresis is nothing but the memory element in the circuit. It means the system or the circuit can remember its previous state, and how much it can remember, that depends on how much is the hysteresis we have in the system. So, we have this hysteresis, this is called the butterfly graph. Let us discuss this butterfly graph for a moment. So, this is called the meta stability. So, we just discussed that we have this butterfly graph, y axis is the voltage and x axis also is the voltage. For example, this is how a butterfly curve actually look like. Now, if we closely see, we have these two loops here, and if we hypothetically try to fit a square in this, let's say this is the biggest square I can fit in this loop, this is called the static noise margin, or SNM. This is called the static noise margin, which is very important to handle the noise in the system. It dictates how much noise our circuit can handle without corrupting its data. So, that is called the static noise margin. So, SNM static noise margin is a major parameter in the design of a static RAM cell. It helps a designer determine the ratio of pull up, pull down, and pass gate transistors. So, this is the static noise margin. Similarly, we have other important parameters derived from this butterfly curve. Let's draw this graph again. So, this is V out, this is V in. So, we have actually two graphs here. One is this characteristic and the other one is for the another transistor. So, these points where the slope is unity, these are called unity gain point, and this value at the input is called VIL, and this value at the output side is called VOH or V output high, and for the other graph the same, this value is called VOL, and this value is called VIH. So now we have these four important parameters which are very important for designing of or connecting of various gates together. We have VIH, VIL and VOH, VOL. So from this butterfly curve, based on the unity gain points, if we project this point on the x axis, we get VIL and VOL, and if we project these points on the output or the y axis, we get VOH, VIH. These are four very important parameters: VIH, VIL, VOH, VOL. These are, as the subscript says, VIH is nothing but input high, the voltage at which input is going to be detected as high. VIL is the low voltage at the input, VOH is the high at the output, VOL is low at the output. These are very important definitions, and we will go through these definitions after 2-3 lectures when we will discuss how do we design a circuit using multiple blocks and we connect them together. During the connection of these different modules, that time we pay very much attention to these VIH, VIL levels, because these are the ones most of the time the error lies in interfacing these ICs or these components together. That happens because of mismatch in VIH, VIL levels. So these are very important parameters which you can calculate from these butterfly curve. These are generally specified in the cell specification document or CSD. Whenever we buy a product or some ICs from the market, in the definition or that CSD document, these levels are very clearly specified. While making an electronic system, you have to carefully see all these levels of VIH, VIL, and they should be compatible to each other. Of course, the voltage, the supply voltage is also one concern, but VIH, VILs are equally important. So these definitions we will come back later at some point of time. These are the definitions we can derive from this VTC curve of metastable circuits such as cross coupled inverter. Now these are the circuits which has hysteresis. It means they, for the going up there is another path, and going back, going down, it is a different path. It means it has certain memory or hysteresis. Where these hysteresis are very much used, for example, when we make normal circuits, when we want to do some data processing at very fast rate, this hysteresis is undesirable thing. We don't want a system or a circuit to have some memory so that it can act fast based on the present input, it can fast provide the output. It should not have any memory or hysteresis, which is a desirable thing. However, in certain applications this hysteresis is very much desired. So most of the circuits we don't want hysteresis, it is a bad thing, but for certain applications we want this hysteresis, we want this memory, so that we can kind of reject some noise, or there are so many applications where we want purposely this hysteresis to come there, and we can design these latches in a lot of different architectures to have maximum and maximum hysteresis for that application. So let us discuss one of such application which needs hysteresis in the circuits. So, the very important circuit which is called CMOS Schmitt trigger. So, Schmitt trigger has so many circuit architectures. You can make in many ways a Schmitt trigger. Let us discuss one very widely used Schmitt trigger or very circuit. So, the first stage here has two PMOSes in cascade and two NMOSes as pull down, and all of these gates are connected together. This is the input, and from this point, the midpoint, we have output going outside, and there is a separate structure connected here, which is a PMOS on top and NMOS at the bottom. This is connected to VDD and this is ground. This NMOS is connected here. So, this is a simple Schmitt trigger structure which is very widely used. So, the very first question is where actually we use these Schmitt trigger and why these are very important circuits. So, in many applications, for example, we have a chip which we want to connect to another chip on a PCB or in a substrate. How do we connect it? We lay down a wire, a piece of metal from one pin of the circuit to the another pin of different IC. Now, this track or this wire has certain length which is very long compared to the circuits inside. Inside circuits are in micrometer range. So, this wire which is in let us say a few inches is very big in magnitude compared to the circuits inside. So, this wire is very prone to the noise generated from the surroundings. This let us say we are transitioning a 1. So, this has so much of noise actually associated from the environment. So, this signal is not a very smooth signal, this has certain noise element superimposed on the signal itself. Now, if this signal which is going from chip 1 to chip 2, if this signal is noisy and second chip is going to detect this signal, this chip does not know whether this is a signal or whether it is a noise in the signal. For the second chip, the signal itself is changing, it does not know it is changing because of the intentional data change or it is changing because of certain noise which is superimposed on this logic. So, to filter this out, to kind of deal with this noise, we use this kind of Schmitt trigger, these type of circuits, and these are generally used as a receiver in the chip. If you buy the chip, generally the outside periphery is the pin. This pin goes inside the chip. When it is connected to the chip, the very first circuit which sees this connection is the Schmitt trigger, or we call the receiver. This receiver is nothing but a Schmitt trigger which has certain amount of hysteresis to reduce this problem of noise. Let us see how this happens. So, for example, we have signal let us say in the same axis we are seeing this is time axis, this is input, and my signal is changing along with the noise let us say this is my signal which is coming in. Hypothetically, let us say if I have a inverter which I do not have a Schmitt trigger, I just apply this to an inverter, what will happen? For an inverter, we know that the switching point is middle of the supply voltage. So, for example, this is the, let us say, VDD. VDD by 2 is the threshold value or the transition value. At this midpoint, inverter going to trip. So, what will happen? If we see the signal, actually this is the superimposed signal with noise. However, the actual signal is just going up and going down. The original signal does not have noise, but because of the environment we have this noisy signal. If we see at this point carefully, before this point my inverter is going to detect it as a 0. Let me take different color. Okay. So, if I have inverter, so this yellow color what I am taking, this is for the inverter. So, at this point the signal has crossed the threshold. So, inverter is going to detect it as a high at this point. However, when it is above this level, inverter will keep this high. As soon as this signal goes below this threshold for a very small amount of time, if we see this signal is going below this threshold voltage, so the inverter immediately will detect this as a transition in the data. However, this is not because of the data, this is because of the noise. We have this small noise superimposed on the data. So, at this point what will happen? Inverter will immediately switch down to 0, and as soon as the data again, this signal again goes above this threshold voltage, it will again trip to the high value and will continue till high, till the blue is above the black curve. Again here at this point, if we see, at this point this has come down. So, inverter will detect it. Let us say I am taking kind of similar logic, here it is 0, so here it is 0. However, it should be opposite, but anyway. So, this goes down again, this is going above this threshold, it will go back again high, and this is because of the noise, this will remain high, and then finally it will go down to 1 to 0, and this will continue. So, this is the detection happened in case of inverter, which is full of error because the data has not changed like this. Data is changing something like this only, but because of the noise it look like a sinusoid kind of wave, and because of inverter which has a very sharp transition, we now see a glitch in the system. This is a very sharp transition over a very small time. So, this is a glitch which is highly undesirable in digital circuits, which is because of this error. So, now if we have this Schmitt trigger, what Schmitt trigger does it has VIH and VIL level differently. It means it has two thresholds now. Let us take the green color now, which is for the Schmitt trigger. So, now Schmitt trigger has two detection levels. One is this upper threshold and this is lower threshold. Now, if we see, when the signal crosses above upper threshold, then only the signal will be detected. So, if we plot the curve for Schmitt trigger, my Schmitt trigger is going to detect a high at this point. So, output will go high at this point, and because now signal is again going below this upper threshold, but the Schmitt trigger will not detect it as a low till this signal reaches lower Vt. So, if we have this small amount of noise in the system itself, that noise is not going to do anything because this noise is not crossing the lower Vt of this Schmitt trigger. So, this will not be detected and the signal is still detected as a high. This will be still detected as a high, and at this point where the lower Vt is reached by this blue curve, that time the output will be detected as a low and it will remain low till this is again crossing the upper Vt. So, this is like this. So, this is how a Schmitt trigger actually handles the noise, because in environment, outside environment, it is full of noise. Noise can come in all the signals. However, the magnitude of this noise is small compared to the full swing of the signal, let us say 0 to 5 volt. Noise is in few millivolts. So, this few millivolt noise can create problem in case of inverter if we put directly to the inverter. However, if we have a Schmitt trigger which has two different threshold VIH and VIL levels. So, because of these two different thresholds, it can filter out the amount of noise from the system, because the input noise, which is very small, let us say few millivolt, is not going to cross over from upper Vt to the lower Vt. So, the voltage range between upper Vt and lower Vt is the amount of hysteresis in the system, and this dictates how much noise the system can kind of reject from the signal. So, if let us say this is a 200 millivolt of hysteresis, the 200 millivolt difference between upper Vt and lower Vt, it can reject 200 millivolt of noise from the system. So, this is how, this is where, this is very practical example. Most of the ICs has receivers which is made up of Schmitt trigger. So, this is one of the very good application of these logic gates. This is all for today. Thank you.